Hello everyone and welcome back to another video. What I'm doing today is mostly meant as a sort of community service because this is a tutorial that I wish existed a couple days ago as I figured all of this out. So, what is this that I've been figuring out? Well, I've been trying to figure out the cheapest and least wasteful way to update an old 8-bit 3D printer mainboard to Klipper. That means reusing the old board and not going to a newer 32-bit board. This means that we also have to install a bootloader onto the old board since they tend to not have them. And also we will not be using an Arduino or external USB flasher, we'll be using the Raspberry Pi that Klipper requires anyway to do all of the firmware flashing. That way we avoid spending money and creating e-waste by getting a new 3D printer mainboard and an Arduino that we'll just use once and then never again, or the same thing for an external USB flasher. Now, in past videos I have talked specifically about throwing out these old 8-bit control boards from my 3D printers, and at the time I had a valid reason, because these boards do not have native support for automatic bed leveling, a feature that I consider to be essential. You should not have this these days, it is pretty much required. And at the time I was aware you can retrofit these 8-bit boards to have automatic bed leveling. I just was very unaware how that would work and thought it would be more convenient to just buy a newer board and then enjoy all the other quality of life things that come with it. However, now I know that really all you need to do is get a little extender dongle that just clips onto your display connector and then rewires the pin that's normally used to activate the buzzer in your display to instead activate the bed leveling probe. The Z end stop will then be repurposed as the signal part of the probe, and just like that you have support for automatic bed leveling, which means that this board now does everything that I think a modern, well printing and fast 3D printer requires, because modern and fast 3D printers run on Klipper. And Klipper doesn't really care how powerful the CPU is, so even if you have this old 8-bit one, it doesn't really matter. You're not even gonna come close to maxing this out, and a 32-bit CPU for Klipper is just overkill. If you're using Marlin, there is a real reason to get a board with a 32-bit CPU, since Marlin runs completely just on the 3D printer itself. But Klipper uses something like a Raspberry Pi as an external single board computer to do all of the heavy lifting. Now, this example is, again, another example of the philosophy of just use what you already have. This is a Raspberry Pi 1, which is good enough to do all of the firmware and bootloader flashing that we'll be doing today, but this is actually not fast enough to run Klipper itself. You want a Raspberry Pi 3 or better for that. Now, I have a Raspberry Pi 4 that's already deployed running Klipper, but I don't want to pull that out of service to make this video, so instead I'm just going to use this Raspberry Pi 1, since, again, the flashing works with any Raspberry Pi that just has 4 GPIO headers available, and this one has a lot more than that. Depending on which exact Raspberry Pi you're working with, the pinout might be slightly different, so make sure to look up an exact pinout for the Raspberry Pi model that you have, so you know where to plug things in later. Other than that, the process is going to be exactly the same regardless of what Raspberry Pi you have, and technically this will work on any AVR device. Not just 3D printer mainboards, not just 8-bit 3D printer mainboards, just anything that communicates using AVR. However, in this specific example, I'll be flashing a bootloader and Klipper onto this Creality 3D 113 board. Outside of the board and the Raspberry Pi, the things that you need is an SD card for the Raspberry Pi, a way of connecting the SD card to your PC, and a set of jumper wires. Now, I didn't have any female-to-female ones, so I used some screw terminals and some female-to-male ones to make a set of female-to-female ones. Looks a bit sketch, is a bit sketch, but works. But yeah, really all you need is 6 female-to-female jumper wires to connect the Raspberry Pi to the ISP slot on the 3D printer board right here. And with that, we have the hardware requirements covered, so let's look at the software requirements right after this message from our sponsor. PCBWay is celebrating their 10th anniversary with their badge design contest. Celebrating a decade of innovation with PCBWay and enabling you to win prizes by designing a badge celebrating PCBWay's achievements in the last 10 years and those still to come. They are offering free prototyping services for badges that meet their design requirements, as well as a $50 PCBWay coupon. And if they like your design, they will feature it on their channels, and it might even become their official 10th anniversary badge. Submissions are open until May 31st of 2024, and the winners will be announced in June. And as always, PCBWay is available for all your PCB prototyping and assembly needs. You can quickly go through their simple ordering process, receive a quote, and have your design be ready for shipping as fast as within 24 hours. PCBWay also offers flexible PCB options, SMD stencils, CNC machining, 3D printing, and injection molding. So whatever part you need, you will probably find an option at PCBWay to get it made professionally. I am very thankful for PCBWay's sponsorship, as it helps immensely with running the channel, and it is a service that I would actually use. So if any of this interests you, please go ahead and give PCBWay a try. So, welcome to the desktop, and here is the 4 pieces of software that we're going to be using today. First, the Raspberry Pi imager to just put an OS image on our SD card, PuTTY to connect to the Raspberry Pi once everything is installed, Arduino IDE to get the bootloader file for our specific chip, and FileZilla to copy and paste files onto the Raspberry Pi remotely. So first off, we'll connect the SD card to our PC, which is what I've already done using a little dongle, and open Raspberry Pi Imager. There you can choose which Pi you have. Like I said, I'm using a Pi 1. Choose the operating system. For this first step, I'm going with Raspberry Pi OS Lite. Choose the storage, here's our SD card. Press next, edit some settings, and here you can edit some settings that you want. You can give the Raspberry a specific host name. This is important later, since you'll have to find the IP address of your Raspberry Pi later, and if you want to do it by just logging into your router and looking at the device list, keep this name in mind. You can also set a username and password, which you'll be needing to log in via PuTTY and FileZilla. You can also configure wireless LAN. If your Pi has Wi-Fi, the Pi 1 does not have Wi-Fi, so I'm not configuring this here, but if your Pi does have Wi-Fi, you can use that instead. I'm going to just use an Ethernet cable today. In services, make sure that SSH is enabled, and then in the options you can configure some more stuff that you like. When you're done, press save, press yes again, and then you only have to wait for the Raspberry Pi imager to do its thing. Now Windows is going to give you this error message. Ignore that, that is fine, that will always happen when the Raspberry Pi imager is imaging your SD card. The imaging onto the SD card is now done, and as it says, you can now remove the SD card from the reader. With the SD card done imaging, we can now connect it to the Raspberry Pi. Then connect the Pi to the Ethernet if you need to. And finally, connect power. The Pi does now turn on, and it will take a couple minutes to boot up and restart. If you want to see more closely what exactly the Pi is doing, you can connect the display to the HDMI port to see its output. You can also connect a USB keyboard to input commands directly onto the Raspberry Pi, but we'll be using PuTTY and FileZilla today since that is easier, giving us the ability to copy-paste commands. For the next step, we'll need to find out the IP address of the Raspberry Pi. The easiest way to do this is probably just to log into your router and look at the device list until you find your Pi. Then note down its IP. As you can see here, for my Pi, the IP address is 192.168.178.53. If you chose to connect the display and keyboard to your Raspberry Pi, you can also directly input the command ifconfig after logging in, which will show you the IP address of the Pi. Once we know the IP address of the Raspberry Pi, we'll open PuTTY and input the IP address. Then we'll press open, and as long as the Raspberry Pi is online and correct, it will try to connect. If you connect your Raspberry Pi for the first time after imaging, you'll get this security warning. For this, just press accept. Then you'll be prompted to log in as your username and password that you preset in Raspberry Pi Imager. Once you are logged in properly into PuTTY, paste this command into PuTTY by right-clicking sudo apt-get install avrdude. Then press enter. This installs avrdude, the program that we'll be using to communicate with the CPU on our 3D printer board. During the installation, it will ask you this yes or no question to get more storage space. For this, just type Y and press enter. Once done, you can use the command avrdude-v and press enter to verify the installation was successful. You should be seeing a screen that looks like this. With avrdude properly installed, we are now ready to connect the 3D printer mainboard to our Raspberry Pi. So, now we will be removing the top cover of the Raspberry Pi to access the pins. And now I can use my monstrosity of jumper cables to connect to the ISP socket on the 3D printer board. Like I said before, now it is time for you to look up the exact pinout of your specific Raspberry Pi model, so you know which of these pins are the GPIO pins. Specifically, I'll be using GPIO pins 17, 18, 23 and 24. I'll be putting up a better diagram of this on screen since it is a bit hard to show on video, so you know what exactly to connect to what. Once you connect the VCC and ground pin, you should see this little LED light up. The wiring part is now done, and we should now be able to check if avrdude can talk to the CPU on this board. Before we can talk to the CPU, however, we first need to configure something in the program. Specifically, we need to tell the program which GPIO pins we just connected to the CPU. So first off, we're going to copy the GPIO config file using this command. And then we will edit it using this command. Once the file is open, hold Ctrl-V to go all the way to the bottom of the file. At the bottom, paste this section. Here we are defining which GPIO pins we assigned to which pin on the board. Specifically, we still need to change the reset pin since I'm using pin 17 instead of 12. The rest of the pins are as I used them, however. Once this is done, press Ctrl-O, Enter to save, and then Ctrl-X to close the file. Now that we've told avrdude how to communicate with the CPU, we can test and see if it can see it by pasting this command. In this command, you need to specify which exact CPU you have. In our case, it is the Atmega 1284P, so make sure you know which exact CPU is on your board. If everything has been corrected and configured correctly, you should get the message AVR device initialized and ready to accept instructions. If you don't, check your configuration and your wiring as something might be broken. This is actually where I got stuck for a long while due to two of the wires that I've been using just being broken and not getting a connection. For the next step, we need to acquire the bootloader hex file that we want to burn onto the board. For this, we will use Arduino IDE. By default, Arduino doesn't include support for the Sanguino style chip and board that we have, so we manually need to tell it to include it. To do this, we need to go to File, Preferences, and then other additional board manager URLs. We need to enter this URL. Just like everything else, it will be pasted in the description of this video, so you can easily copy and paste it. Once that is done, go to Tools, Board, Board Manager, and then scroll down the lists until you see the Sanguino board and press Install. This will download all the required files, including the hex bootloader file for our Atmega 1284P. To actually get the hex file, open your Windows search bar and type %appdata%, then press Enter. This brings you to the roaming folder inside of the hidden app-data directory. Go up to app-data, then to Local, Arduino 15, Packages, Sanguino, Hardware, AVR, 103, Bootloaders, OptiBoot, and find the hex file corresponding to your specific CPU. In our case, that would be the OptiBoot Atmega 1284p.hex. Next, copy this hex file somewhere safe, and now we'll be using FileZilla to transfer it to the Raspberry Pi. FileZilla works in a similar way to PuTTY. You put in the IP of the Raspberry Pi, put in your Raspberry Pi username and password, and enter the port of 22. Then press Quick Connect. Now just drag the hex file into FileZilla, which will paste it onto the Raspberry Pi. Next we go back into PuTTY and paste the flash command. Again, here you need to specify which exact CPU you have, as well as the file name of the file that we just copied into the Raspberry Pi. Once this is done, just press Enter and it should now flash the bootloader onto your board. And just like that, our board now has a bootloader. That means the first part and the most complicated part of this tutorial is now done. Similar to the bootloader, you can also flash any firmware you want onto AVR chips this way. However, we just want to use a bootloader this way, since now we'll be using a much easier method for flashing any other firmware that we need. Now that we have the bootloader on our board, we can now go back to Raspberry Pi Imager and re-image the SD card. As an operating system, this time I won't be using Raspberry Pi OS Lite. Instead, I'm going to go to Specific Purpose OS, 3D Printing, and choose Mainsail OS. This, together with Fluid, are the two most popular Klipper operating systems. Mainsail OS, as you can see, is directly available in the Raspberry Pi Imager, whereas Fluid can be installed either by downloading the Fluid Pi image off of the Fluid website and then using it as a custom image in Raspberry Pi Imager. However, this is not recommended by them since they are no longer directly supporting it. Instead, they recommend that you download and run the Yahoo GitHub script, in which you can manually install Klipper, Moonraker, and then Fluid. To keep this video as simple and short as possible, however, I will just be using the Mainsail OS option directly in Raspberry Pi Imager. Again, edit the settings to your liking, and then just wait for it to write and verify. Now here we have our SD card now flashed with the brand new Mainsail OS image. Just connect that back to the Raspberry Pi. And since we now have a bootloader on our mainboard, we can simply connect it to the Pi over USB. Connect power back to the Raspberry Pi and give it a few more minutes to boot up. Once the Raspberry Pi is done booting up, it will also start hosting its web interface. To access that, simply put the IP address of your Raspberry Pi into your browser. For now, it is reporting an error that no printer.cfg file is present, which is normal. Right now I want to use this opportunity to update Klipper and all the other software present on the Pi, which you can simply do in the Machine and then Update Manager section. This updating process will take some time and will end in Mainsail restarting. Once Mainsail has properly restarted, it will show you a message that all updates are done. Once you are done updating Mainsail, go back into PuTTY and log in. It is now time to compile and then flash the Klipper firmware onto our 3D printer board. Start by copy-pasting this command. And then the next one, which is make menuconfig. This will bring up a small GUI in which you can select which exact CPU you have on your board. The 8-bit Creality board has an Atmega AVR CPU, which is already selected correctly, but the processor model is different. Like I said before, we have an Atmega 1284P. So we select by pressing Enter, then pressing Q to quit, and Y to save configuration. The next command is just make. This will now compile the Klipper firmware for our 3D printer board. Once done, it will report that the Klipper elf.hex file has been created. Next, we will ask the Pi to list all USB devices connected. As we can see, our 3D printer mainboard has this address. Next, we will stop the Klipper service, and then we will paste the command make flash device equal. After the equal, we will need to put the address of our board. Copy it simply by highlighting and then pressing right click. Then press Enter, and the firmware should now be flashed onto your 3D printer board. All that is left to do is now to restart Klipper, and you are now done installing a bootloader and Klipper firmware onto your 8-bit Creality board. In Mainsail, we still have the error that no printer CFG is present. Now it is time to upload one. On the Klipper GitHub page, you can find many example files for many different printers and motherboards. In this case, we'll be using the printer Creality Ender3 2018.cfg file, as this is made specifically for the 8-bit Creality version 1 boards. In Mainsail, go to Machine, and then press Upload File. Once the file is uploaded to Mainsail, press Rename, and set the name to simply printer.cfg. In order to make sure that the printer properly interfaces with Mainsail, go to the printer.cfg file and add this line, include mainsail.cfg. This enables functionalities such as the virtual SD card, being able to print G-code files directly from the web interface. Now press firmware restart. If everything worked correctly, you will now get an ADC out of range error, since our motherboard is not connected to a 3D printer and is reporting a whole bunch of garbage data. You should now also be able to see the Atmega 1284P load in the system loads section. This means that our motherboard is now correctly connected to the Raspberry Pi and that Klipper is running normally. Next, you would install the motherboard into your 3D printer as normal, and since the printer.cfg file we have downloaded is already done and ready to be used with a Creality 8-bit board, that now concludes the entire tutorial. You are now ready to use your Ender 3 or similar with Klipper. And there you have it. You now have a Creality 8-bit board running a bootloader and Klipper, as well as a Raspberry Pi host machine. And now of course you can enjoy all the comforts of Klipper, such as being able to edit the printer.cfg file at any time you want by simply making the edits you want and then pressing save and restart. No firmware flashing required. And while this specific example in the video was just that, an example, I do actually own a Raspberry Pi 4 that I've done this exact thing to, that is currently also connected to an Ender 3 that I'm upgrading, which still has the original 8-bit board inside of it. And after using it for a while, I have to say that the experience is exactly the same as using an upgraded 32-bit board. There is really no reason to throw this out unless you really need something specific from the newer 32-bit boards. So if you're on a tight budget, or you're someone who just doesn't like creating unnecessary e-waste, you can keep the old 8-bit board just fine, tinker with it a bit to make it have automatic bed leveling, and then put the bootloader on it, and you're good to go printing just like everybody else. And keeping that philosophy alive, we did all of this using just a Raspberry Pi, no Arduino or external programmer required. And that is all. So, thank you all for watching. I hope this was helpful to you. A guide like this would certainly have been helpful for me, since I spend way too much time trying to get this to work, and what you just saw was a combination of 3 or 4 different guides all packaged together. Now yeah, this was specifically for flashing an 8-bit 3D printer mainboard from Creality, but the bootloader flashing process also works for regular firmware that's not just a bootloader on any AVR device. So feel free to adapt this for anything you want. With that though, I think this video is now long enough, and with that, until next time, goodbye. Oh yeah, if you're wondering what happens when you try to use a Raspberry Pi 1 to actually run a full 3D printer with the board installed, you just get this error. Timer too close, the Raspberry Pi is too slow, you can see the CPU spiking to 100% every couple seconds. Yeah, you just kind of need a Raspberry Pi 3 or better for this.